Today we're going to dive into the story of a particle that, on paper, shouldn't even exist. I mean, it was like a ghost hiding in the equations of physics that, incredibly, turned out to be real. We are talking about the positron, the very first piece of antimatter we ever found. So what is the opposite of matter? I mean, it sounds like some deep philosophical question, right? But for physicists, it's a very, very real one. And the answer isn't nothing. Nope. It's something called antimatter. And our story, well, it kicks off with the very first bit of it we ever laid eyes on.
Okay, so what exactly is a positron? Well, the easiest way to think about it is like an electron's identical twin, but with one crucial difference. It's got a positive charge. Everything else is the same mass, same spin, just a totally opposite electrical personality. But, that simple definition, it hides an absolutely mind-bending origin story.
Yeah, this whole journey begins, believe it or not in a fancy lab, but on a piece of paper. It starts with an equation that was holding a secret that nobody, and I mean nobody, was prepared for. So back in 1928, this brilliant physicist, Paul Dirac, he decided to take on this just massive challenge. He wanted to merge two completely different worlds, quantum mechanics, the physics of the super tiny, with Einstein's special relativity, the physics of the super fast. And you know what? He pulled it off. He created this beautiful equation that perfectly described the electron, nailing even its weird property called spin. It was, without a doubt, a monumental achievement. But there was a catch, a big one. See, his equation, kind of like how the square root of 4 can be +2 or -2, it had two solutions. One solution was the electron we all know and love, but the other one described an electron with negative energy. And that just made zero sense. How can you have less than zero energy? It's impossible. This little mathematical ghost was threatening to tear down his entire beautiful theory. And what's really fascinating is just how fast this whole debate moved. At first, Dirac thought, okay, maybe this mystery particle is just the proton. I mean, it had the right positive charge. But then Robert Oppenheimer, yes, that Oppenheimer, pointed out a pretty fatal flaw. If that were true, every hydrogen atom in the universe would basically just self-destruct instantly. So, back to the drawing board. And in 1931, Dirac took this enormous leap of faith. He proposed that his equation wasn't wrong, it was predicting a brand new, never-before-seen particle, an antielectron. This idea was so out there, so strange, that it led to even wilder interpretations. The physicist Richard Feynman later came along and showed how you could look at the math in a completely different, and frankly, mind-bending way. He said a positron is just an electron traveling backward in time. Just let that sink in for a second. It's a concept that really truly stretches the imagination. Okay, so making a bold prediction like that is one thing. But actually finding it in the real world, that's a whole different ballgame. So here's the story of how that theoretical ghost was finally caught. So this was the most wanted poster, right? The profile of the particle they were hunting for. It had to be a perfect match for the electron in every way. Same mass, same spin, but with one critical telltale difference, a positive electric charge. And the hero of this part of our story is a physicist from Caltech named Carl Anderson. Now, he wasn't even looking for antimatter. His job was to study cosmic rays, these super high-energy particles that are constantly raining down on Earth from space. And he was using this really cool device called a cloud chamber, which basically lets you see the tracks that these invisible particles leave behind. Now, his setup was just brilliantly clever. He surrounded this cloud chamber with a super powerful magnet. And what this does is it forces any charged particle flying through to curve. Negatively charged particles, like electrons, would bend one way, and any positively charged particles would have to bend the other way. And then he saw it, a track. It had the exact same curve as an electron, which meant it had to have the same mass. But it was bending the wrong way. It was behaving exactly like an electron, but it clearly had a positive charge. He'd found it. It was Dirac's anti-electron. This was the first concrete, undeniable proof that antimatter wasn't just some mathematical quirk. It was real. Theory had finally, officially become reality. And for this discovery, you bet Carl Anderson won the Nobel Prize. So, okay, this exotic new particle was found coming from the depths of space. Sounds pretty rare, right? Well, it turns out you don't have to look nearly that far to find one. In fact, they're surprisingly common. You want to know where positrons come from? Well, they're forged in some of the most extreme places you can possibly imagine. We're talking about cosmic rays slamming into our atmosphere, crazy gamma ray flashes that happen above thunderstorms, even in the powerful jets shooting out from black holes. But they're also created much, much closer to home through something as simple as the natural radioactive decay of certain elements.
Okay, so take a look at this number, 4,000. What on earth could that possibly refer to? Believe it or not, that's roughly how many positrons your own body produces, every single day. They come from the natural decay of something called potassium-40, which is an isotope we all have in tiny amounts inside of us. That's right, you are a natural, walking, talking antimatter factory.
So, how do we actually use a particle that started out as just a weird little puzzle in an equation? Well, today it's an absolutely key tool in both cutting-edge science and, believe it or not, life-saving medicine. Yeah, the most famous application by far is the PET scan. That stands for positron emission tomography. Here's the rundown of how it works. First, a patient gets a special radioactive tracer that, you guessed it, emits positrons. This tracer is designed to gather in places with high metabolic activity, think cancer cells. So these positrons get emitted, they immediately bump into a nearby electron, and boof, they annihilate each other. This annihilation creates a pair of gamma rays that shoot out in perfectly opposite directions. A big scanner then detects these rays, traces their paths back to the single point where they started, and builds this incredibly detailed 3D map of what's going on inside the body. It's amazing.
And it's not just medicine. Positrons are also used to probe for tiny, microscopic defects in advanced materials. And at amazing places like CERN, physicists are actually using them to build antihydrogen. That's a whole atom made of antimatter, all in an effort to study the deepest, most fundamental secrets of our universe.
So you see, it all comes back to this one fundamental rule of the universe. Whenever a particle of matter meets its antimatter twin, they annihilate. They just disappear in a flash of pure energy. It's the ultimate cosmic cancellation. And all of this leads to one final, absolutely massive question.
And that leaves us with maybe the biggest mystery of them all. See, the Big Bang should have created equal amounts of matter and antimatter. But if it did, they would have all just canceled each other out, annihilating everything and leaving behind a universe filled with nothing but light. So why are we here? Why is there anything at all? Why did matter win out in the end? That tiny, tiny imbalance from the dawn of time is still one of the greatest unsolved puzzles in all of science.